Good evening, everyone. I welcome you all to the problem solving session 11 for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Hyderabad. And the live session is handled by myself, Anchor Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. Sorry, the professor is from IIT Guwahati. So, this live session is from 6 p.m. to 8 p.m. every Friday. So, we have reached almost the end of the sessions. So, that is week 11. So since this is a 3 like 4 12 weeks course, so we have almost reached week 11 of the course. So yeah, I think it's time, so we'll start. Sorry. Okay. So the course layout is as structured as this. So in week 1 to 2, we saw what fluidization is and what are the advantages and disadvantages of fluidized beds and what are all the industrial applications of fluidized beds. So what is fluidized beds? Fluidized beds are nothing but when we pass the fluid inside the packed bed at a sufficiently high velocity so that the particle starts to behave like a fluid. So when we are imparting fluid like behavior to the solids, we call it fluidized beds. So what are the advantages of fluidized bed? Because it is using the particles as a solid medium, sorry, the particles to behave like a fluid medium, we can avoid hotspot formation when we are using fluidized beds. Because in packed bed the major disadvantages such that there are chances for hotspot formation, which is completely avoided when we are using fluidized beds. And what if and so it also evens out the enhances the mass transfer rate for the solids, catalytic reaction and all. But what would be the disadvantages when we are dealing with fluidized bed? If it is completely advantageous, we can always prefer fluidized beds to packed beds, right? So the thing is, in fluidized beds, the chances of the catalytic erosion, that is the particle erosion, is very high. So, and also like in certain reactions, when we are using highly costly catalysts are very costly, as you all know. So, in those cases, it would not be efficient to prefer fluidized beds. So that is one disadvantage. And where all we find applications of fluidized beds? Fluidized beds is very much used in chemical engineering industries like various homogeneous heterogeneous reactions, biomass gasification, everything uses fluidized beds. So it is very much essential to understand the phenomenon of fluidized beds. So all those things we have seen in the weeks 1 and 2, and followed by we study the characteristics of solids and classification of solids. So when we are dealing with the fluidized beds, it is such that not all solids behave same inside the fluidized bed. So the what are all the properties of solids that would generally differ? The solids would differ by size, shape, and their density, like when we are looking into their physical attributes. So depending on the size and density, Gellert classified them into 4 classes: A, B, C, and D. So the very fine particles, that is the smallest of particles with very uh, comes under Gellert C. So these particles would be cohesive in nature. Imagine them sticking together. So it is very difficult to fluidize because they rise together and move together because of their cohesiveness. So it is very much difficult to fluidize these particles. And next is with a little increase in size comes the Gel-Dot A particles. These are very much used in industries because they do not have bubble formation on one side, and also like they are easy to fluidize compared to Gel-Dot C particles. So as you all know, FCC catalyst, the catalytic, the cracking catalyst comes under Gel-Dot A, and with much more increase in its size, we come under Gel-Dot B particles. These Gel-Dot B particles are also widely used and they are prone to bubbling. That is to be noted when we are dealing with gel dot V particles. But the last category, that is the very largest of particles, comes under the gel dot D particles. These gel dot D particles are very difficult to fluidize, and also they are leading to spout, like they are used in spouted fluidized beds, because it is not easily used in gel dot D particle normal fluidization. Gel dot D, because of their large size, it is easier to form very big bubbles. So depending on their properties, the particles would be used in different applications on the requirement basis. So, and also flow characteristics, and it's outlined in different types of fluidization. So when we are passing the fluids inside the bed, depending on the velocity or excess velocity, the regime of fluidization is completely varying, and that was seen in the week 4 to 5. Flow pattern of fluidization system, flow pattern transition, flow pattern map, frictional pressure drop, and etc, etc. So what exactly happens is that with the fluids can be liquid or gas. So in liquid solid fluidization, we mainly observe homogeneous or smooth fluidization. Whereas in gas solid fluidization, it is observed bubbles formation is very quite observed. When we are passing the gas inside the fluidized bed, the particles rise, and also with some excess, small bubbles starts to form. This is known as bubbling regime. With time and with increase in velocity, the bubbles grow in size, and that they almost reach, the bubbles grow in size and reach the size of the column. And once after it is reaching the size of the column, it starts to break down, and because of this breakdown, the solid particles are also easily circulated. Like there would be a carrying over of solids in the wake of the bubbles, and once the bubbles burst, the solids would be dropped down. So this type of circulation happens inside the fluidized bed also. So what are all these regimes? Initially we would call it bubbling regime, and then with increase in some bubble size, it is slugging and axial slug, and then it grows almost towards the size of the column, and then after that it is turbulent regime, and with breakage of bubbles, we call it fast fluidization regime, and at last we have the particles needs to be recirculated. So pneumatic regime is observed at the end. So the solid movement, mixing, segregation, and staging, everything needs to be known to completely design a proper fluidized bed, because depending on the height of the column and all, the movement and the circulation of the solids differs. So with certain velocity range, we have mixing to be observed, and with certain velocity range, we can observe segregation when we are dealing with more than one type of particle. So in industry, generally that would be the case, where we would be dealing with more than one type of a particle. So this becomes important to be studied. And next is the gas distribution system. So in week 6 we saw about the type of gas distributor in small scale and large scale industries, and design of distributor. So what we studied is that what are all the type of gas distribution, how does it affect, because it affects the pressure drop inside the fluidized bed. Therefore it is important to know what type of distributors to be used. For example, we can use porous distributor at a small scale, but in industrial scale, when we are dealing with that, we need to go for perforated distributors or bubble captures and so on. So depending on the type of distributors that we are using, we observe the pressure drop to be varying, and hence the design of that is very important. And at the week 7, it was we were dealing with bubbling fluidized beds, where it is important to study the bubbling fluidized bed, because only then we can understand the interchange between the gas and the solids in bubbling fluidized beds, and how the bubble formation influences the mixing inside the bed between the particles. Everything is very important. And in week 8, it was about entrainment and elutriation from fluidized beds. Entrainment and elutriation is nothing but when we are carrying over the solids, once the terminal settling velocity of the solids is exceeded, those particles would be carried over. That is known as entrainment. And elucidation is nothing but when we are specifically removing certain solid range based on its size, it is that is especially fines, we call it elucidation. So these become important to study because we need to know how much solid might be lost. So depending on it, we need to know the recirculation rate, everything. So entrainment and elucidation from fluidized bed is important because only then we can determine the height of the column to be used so that the solid particles would not be escaping from the bed. And next is the attrition mechanism and its analysis by model. So when we are dealing with solids, since particles are moving against each other, the solids rub against each other and their surface wear and tear occurs. So attrition, and it is important to study that. And so only then we can determine the solid particle loss inside the fluidized bed, which is again important. And week 10 to 11, it is about mass transfer phenomena and particle to gas mass transfer and its analysis by modeling 2 and 3 phase system and modeling. So when we are dealing with the fluidized bed, it becomes completely necessary to study the mass transfer phenomena that is happening inside the bed, because we are dealing with so many phases like solid phase, liquid phase or gas phase, and also the bubbling phase. So particle to gas mass transfer and its analysis by a model is essential. Thereby we are dealing with 2 phase or 3 phase systems and its modeling. Like different models assume some different properties of inside the bed and model them accordingly. And in the last week, it would be about heat transfer phenomena happening inside the fluidized bed, and also the design of fluidized bed reactor for physical operation, catalytic and non-catalytic systems. So this is the course layout. And for the as for the books and references, the first book to be considered very much useful is Cooney and Levenspie's Fluidization Engineering. This we have been seeing and saying, I have been saying from the start of the course that it is an important book to be read. Because it almost covers all the basics that we need to know before we are moving into deal with fluidized beds in our for anything, like for our complete understanding. This is a very important book. And second one is De Gidaspo's Multiphase Flow and Fluidization, Continuum and Kinetic Theory Description. So this book is actually, when we are modeling fluidized beds, we can model it as a continuum. Like when we are modeling the solid phase, we can model it as continuum or the Lagrangian phase. So in Lagrangian phase, we know that we track each individual particles and write their equation and solve them. But when we are dealing with the continuum theory, it becomes necessary to assume certain properties of the solids such that the kinetic theory description, can be applied. So we can formulate kinetic theory of granular flow similar to that we use for kinetic theory of gases. So based on that assumption, it is possible to model the particles as a continuum. So that is explained well in this book along with the other aspects of fluidization. And third is Gibilaro's Fluidization Dynamics. And fourth is Professor K Majumder's Hydrodynamics and Transport Processes of Inverse Bubbly Flow. So till this, that is the course layout and books and references have been repeated in almost all the problem solving sessions. That is just to stress the importance of these and to help those who listen to the lecture for the first time. So now we'll move on to the this week's problem. So this week, as we have seen, it is dealing with the mass transfer phenomena happening inside the fluidized beds. So question 1 is, what is the unit of dispersion coefficient? Meter per second. Option B, meter per second square. Option B, meter per second. Option C, meter square per second. Option D, meter square per second. I guess I'll change the animation pattern because I think it is quite visible for you guys. So just give me a moment. Yeah. Okay, I think it is something to do with this. Okay, guys, we'll just leave it. So I think you guys can see the answer, but however, just think why this would be the answer. So we can, I mean, answer is quite visible, but just think, take a minute to understand what is happening, and we'll discuss the answer. So answer is nothing but meter square per second, which is option D. Because what is dispersion coefficient? Dispersion coefficient is nothing but it is modeled as the product of fluid velocity u and some characteristic length scale. So we know the fluid velocity unit as, I don't know why it is so much shaky. Just give me a moment. Okay, just leave it. I'm not sure what is going on. So dispersion coefficient is frequently modeled as the product of fluid velocity u and some characteristic length scale. So we all know it is meter per second is the fluid velocity unit, and characteristic length scale is m. So it is meter per second into m, which is meter square per second. So this way we can identify the unit of the dispersion coefficient as meter square per second, which is option D. We'll go to question 2. In question 2, it is asked that what is the correct expression for Schmidt number where u, mu, rho and d represents the viscosity, density and diffusivity respectively. So option A, it is Schmidt number is equal to rho g d by mu, and option B, it is mu by rho g d, or option D, it is d by mu g rho, or option C, it is d by mu g rho, mu rho g, or option D, it is mu rho g by d. So I think it is a very easy question for all the people attending. So I think you would be able to answer. Just take a minute and we'll discuss the answer. So actually Schmidt number, the answer is mu by rho GD, which is option B. So Schmidt number is nothing but it is the ratio of kinematic viscosity to the molecular diffusion quotient. So what is kinematic viscosity? That is mu, which is equal to mu by rho, and diffusion coefficient is D. So it is the ratio of kinematic viscosity to the molecular diffusion coefficient. So it is mu by rho by D, that is mu by rho g D. Mu by rho g is the kinematic viscosity and divided by the molecular diffusion coefficient, which is D, or diffusivity, whatever. So this is question 2. We'll go to question 3. In question 3, it is given that which of the following is a wrong statement regarding the mass transfer coefficient under a single sphere condition. So it is proportional to the diffusion coefficient of the gas. It is inversely proportional to the particle diameter. Option C, it is inversely proportional to the mole fraction of the inert component. Or option D, none of the above. So yeah, give the answer and we'll discuss. So actually, Sherwood Sherwood number is given by K into, I don't know why this was blinking this much, kg. So Sherwood number is given by kg, k into d by d. K d, sorry, d, that is diameter of the particle, y, that is mass transfer, divided by d. So what are we observing from this? The mass transfer coefficient is k. So if we take it under that side, mass transfer coefficient k is inversely proportional to particle diameter and inversely proportional to the mole fraction, and again it is directly proportional to the diffusion coefficient of the gas. So all these is the correct, all these are right statements, and correct answer is option D, none of the above. And we'll go to question 4. In question 4, it is given by total exterior surfaces of all individual particles in the bed as per Kuhn-Levenspiel is given by exterior surface of all the particles, that is SEX of particles, is equal to V into segment of the bed, that is V seg, 6 into 1 minus 5s divided by epsilon bed into D sphere, that is the V segment is the volume of the segment of that bed, and 5s is the sphericity of the particles, and epsilon bed is the void fraction of the bed, and D sphere is the diameter of the sphere or equivalent sphere. So total exterior surfaces of all individual particles in the bed as per Cooney and Levenspiel we need to know. So option B, it is V seg into 6 into 5s into d sphere by 1 minus epsilon bed. Or option C, it is V seg into 6 into 1 minus epsilon bed divided by 5s into d sphere. So or option D, it is none of the above. So you need to identify which one is the right statement. So actually on looking at it itself, it is very easy to eliminate certain options. So uh, even if you are not able to give a proper logical explanation, just try to analyze what is happening in the equation. By then you can figure it out. So answer is actually option C. That is total exterior surface of the particles is equal to V segment into 6 into 1 minus epsilon bed by 5s into d sphere. So the thing is we need to associate the 5s with the d sphere, and also like to get the total volume fraction of the particles inside the bed, we are using V segment into 1 minus epsilon bed. That is, epsilon bed is a wide fraction and 1 minus epsilon bed gives the total particle fraction inside the bed. So V segment into 1 minus epsilon bed gives the volume of the particles inside the bed. So divided by 5s into d sphere, that actually gives the total exterior surfaces of the all individual particles in the bed. So that is option C is the right answer. So now we'll go to question 5. In question 5 it is asked that what is the sphericity of the spherical particle. Option A, it is 0.5, option B, it is 1, option C, it is 0, option D, it is none of the above. This is a very straightforward question, so you must be able to give the answer. So actually we know that the sphericity of the particles, that is sphere, is always 1, because we are comparing all the other particles to how closely they resemble the sphere. That is what is given from the sphericity values. So obviously the sphericity of the spherical particles is 1. That is option B is the right answer. So we'll go to question 6. What will be the sphericity of the particles that is not sphere? Option A, it is phi is equal to 1. Option B, it is phi is greater than 1. Option C, it is phi is less than 1. Option D, none of the above. So again, this is a very simple question. So just try to answer it. So as we all said that since sphericity is a factor associated with how close the particles resemble sphere, and the sphericity of a sphere is 1. So all other particles sphericity is actually less than 1. So because we are dividing it by a factor and we are obtaining sphericity, it is always less than 1. So option C is the right answer. Phi is less than 1. So question 7, moving on to question 7, what is the unit of mass transfer coefficient? So option A, meter per second square. Option B, meter square per second. Option C, it is meter per second. Option D, none of the above. Yeah, give the answer. So the answer is meter per second, which is option C. This we can actually look into in the coming up problems, like from there we can solve it. Mass transfer coefficient is unit is required, and yeah, answer is option C. It is not A. So we'll go to question 8. In question 8, it is given, it is a problem. Calculate the Sherwood number for an naphthalene particles of diameter 2.5 mm. Use Rand's expression where data given is U is equal to 0.5 meter per second and density of gas is 1.18 kg per meter cube and viscosity of gas is 1.8 into 10 power minus 5 kg per meter second and Schmidt number is 4.8. So options are 5.55 or option B it is 11.16, option C it is 2.98, option D it is 10.10. So just solve it and I'll give you guys 1 minute time. So try solving it. If not, we'll solve it in the next few minutes. So actually we'll solve it. So as always, we'll write the given data. Particle diameter is 2.5 mm. dP, that is equal to 2.5 mm. So now we need to know which formula to use. So we are asked to find, find Sherwood number. We are asked to use Rand's expression. So the formula actually is number is equal to 2 plus 0.6 into Reynolds power 0.6. Power 1/3. So this is applicable when Reynolds is less than 150 and Schmidt is between 0.5 to 2. So this is the criteria. Schmidt number is 4.8. I think we can leave out this criteria because again it is criteria is wrong or somewhere because this is a formula to be used, and for that first we need to find Reynolds number of the particle. R is equal to rho u by mu, which is equal to 1.18 rho into 0.5 into 2.5 into 10 power minus 3 into divided by 1.8 power minus 5. So what this would give us? 1.18 into 0.5 into 2.5 divided by 1.8. This would be divided by 10 power 2. So it is 81.94. That is the Reynolds number. So now we are substituting in this given formula. shower number is equal to 2 plus 0.6 into 81.94 power 0.5 4.8 power 0.33. So what is this giving us? 1 divided by 2 into 4.8 divided by 1 divided by 3. That is 1.52 into 0.6. Actually, what is the answer? 11.16, right? Eighty-one point nine four power 0.5 into 0.6 into 4.8 power 1 divided by 3 9 okay, divided by 10. So actually answer is 2 plus 9.16, which is nothing but 11.16. So actually the answer is 11.16, which is option B is the right answer. So I hope this is clear. If there is any doubt, please ask, or else we'll move to the next question. So I think it is clear. Now we'll go on to question 9. In question 9, it is given that determine the Schmidt number for naphthalene particle of diameter 1.2 mm with diffusion coefficient 0.086 cm square per second, and data is mu and rho g are given. So mu is viscosity of the gas is 1.8 into 10 power minus 5 kg per meter second, and rho g is 1.18 into 1.18 kg per meter cube. So answers are 1.77, 2.55, 3.98 and 5.87. So for this we'll do as always. So first is data. Data. dp 1.2 mm with diffusion coefficient d is equal to 0.086 centimeter square per second, and mu is 1.8 kg per meter second, and rho is 1.18 kg per meter cube. So we are asked to find Schmidt number. So we all know what is Schmidt number, and formulae is schemic number is equal to mu by rho g d. We saw it is schemic number is the ratio of kinematic viscosity to the diffusion coefficient. So mu divided by rho g. So how do we do? Mu is 1.8 into 10 power minus 5 by 1.18 rho g into d. D is 0.086. Since it is centimeter square, we need to convert. So again it is 10 power minus 4. So on solving this, what we are getting? Answer is actually 1.77, I think. Yeah. Answer is 1.77. So schemic number we have found out to be 1.77. So how did we find? Schemic number is nothing but mu by rho GD. So and substituting all the known values, we are getting the schemic number as 1.77. So if there is any doubt in this question, please ask, or else we will take a short 5 minutes break and resume the session. So we'll go to question 10. In question 10, it is asked that gas is passing at a gas velocity of 0.04 meter per second through a fixed bed of particles 2000 micrometer. Calculate the Reynolds number of the particle where rho gas is given as 1.225 kg per meter cube, mu gas is 1.81 into 10 power minus 5 kg per meter second. Again, it is a very straightforward question. So option A is 10.41, option B is 5.41, option C is 11.41, option D it is 7.41. So I request you all to take a paper and then solve it because it is a very simple straightforward question. We are asked to calculate the Reynolds number of the particle. It is particle Reynolds number. The main thing is that. Other than that, do whatever. Like you can be very clear in that. So we'll solve this. Are there any people in the meeting actually? Why it is so silent? Find. What are we going to find? We are going to find the Reynolds number of the particle. Number or particle Reynolds number, whatever it is. Formula, what is it? Formula rho VD by mu P. it is rho u dP by mu gas. So which is 1.1 it is 1.225 into u is 0.04 into 2000 into 10 power minus 6 divided by 1.81 into 10 power minus 5. So what this would be 1.225 into 1.225 into 0.04 into 2000 1.81. It is 5.41. I'm getting weird answer. I don't know whether it is in the option or not. Yeah, answer is 5.41. REP is 5.41. So in this question, we are asked to calculate the Reynolds number of the particle. So the formula for which is REP is equal to rho V dP by mu. So all the given data are given in the question itself. So we have used the formula and we have obtained the answer as 5.41. So I hope the answer is clear. If not, just take a minute to look at it. It is a very straightforward, simple problem. So it must be very clear. Yeah, we'll go to next question in a minute. So this will now move to question 11. In question 11, it is asked that a fluidized bed of length 0.60 meter and width 0.25 meter and depth 0.04 meter is filled with a spherical particle of 0.5 mm. The voidage of the bed is 0.45. Determine the total exterior surfaces of all particles in the fluidized bed reactor. Use the Cooney and Levenspils 1991 expression. So option A it is 39.6 meter square. Option B it is 19.6 meter square. Option C it is 29.6 meter square. Option D it is 79.6 meter square. So this formula we have seen in the previous problem as one of the question where we were asked to choose it from the answer. So similar to that it is given. So it is just a matter of calculation. I mean substitution and calculation. So just feel free to substitute the given data in the previous formula and solve it. Try getting the answer and if possible share it. We will just look into the answer in a minute. So this 1 minute is for you guys to analyze the question and solve for the answer. So we'll solve this. For solving, first we'll write the given data. So bed dimensions, L is equal to 0.60 meter, and width is equal to 0.25 meter, and depth is equal to 0.04 meter, and it is filled with spherical particles of size 0.5 mm. dp is 0.5 mm. And voidage of the bed is 0.45. We are asked to find the total exterior surface area of all particles in the fluidized bed. So we are asked to find S particles. So so we'll take the formula from the previous question. Yeah, this one. It is by. So we need to substitute in this. So for V, I mean first. First we need to find V segment, that is volume of that particular segment, is equal to 0.6 into 0.04. So 25 into 4, it is 100. 100, 1.01. So it is 0.006 is the volume. It is meter cube, and phi is actually, it is 1. Because it is sphere. So remaining thing, it is 0.006 into 6 into 1 minus 0.45 divided by d sphere. We can keep it as yes also. Yes. Pi into 10 power minus 3. So what is the answer? 0.006 0.006 into 0.55 into 6 divided by 0.5. It is 39.6 meters square. I hope the answer is correct. We will check the answer. 39.6 meters square. So what are the given things and how did we calculate the answer in this particular problem? We have the bed dimensions and we know this particle sphericity, that is equal to 1 for sphere, and diameter of the particle is given and voidage of the bed is given, which is epsilon d at bed. So we know this total exterior surface area of the particles formula as this, that is V segment, that is volume of segment into 6 into 1 minus epsilon bed divided by pi s into d sphere. So on substituting all the given things in the above formula, we are getting the perfect answer. That is 39.6 meters square, which is option A. So option A is the right answer. So now we'll go to question 12. In question 12, it is asked that select the correct expression for the interchange coefficients, where KBE, KBC, KCE denote the interchange coefficient between bubble and emulsion, bubble and cloud and emulsion respectively. So KBE, that is interchange coefficient between bubble and emulsion, is equal to KBC plus KCE by KBC into KCE. Or option B, it is KBE is equal to KBC plus KCE divided by KBC minus KCE. Or option C, it is KBE is equal to KBC minus KCE by KBC plus KCE. Or option D, it is KBE is equal to KBC into KCE plus divided by KBC plus KCE. So this is similar to the problems that we deal. So just find out the answer. We will discuss how that is the correct answer. So actually the answer is KBE is equal to KBC into KCE by KBC plus KCE. So what we are that is option D is the right answer. So what we are dealing with is the interchange coefficient between the bubble and emulsion is equal to bubble into cloud into emulsion by bubble into cloud plus cloud into emulsion. So normally how do we if you can remember, we just deal with the interchange coefficient as this. If you take reciprocal, it would be very easy for you because it is 1 by KBE is equal to 1 by KBC plus 1 by KCE. So in that case, 1 by KBE is equal to KBC plus KCE divided by KBC into KCE. So on taking the reciprocal, we are getting KBE is equal to KBC into KCE by KBC plus KCE is the right answer. That is option D is the right answer. Actually, my pen is not writing in this properly, so that's why I cannot write and explain. So I hope you people can visualize everything whatever is being said. If not, just let me know. I'll think of some other way. So the answer to this question is KBC into KCE by KBC plus KCE, which is the right answer. That is option D is the right answer. We'll go to question 13. In question 13, it is asked that what is the unit of interchange coefficient between bubble and cloud? That is KBC that we saw in the previous problem. Option A, it is meter square per second. Option B, it is 1 by second. Option C, it is meter per second square. Or option D, it is none of the above. It is interchange coefficients unit is as. So you pick one from the four options and we will discuss. So the right answer to this question is 1 by second, that is option B is the right answer. The interchange coefficients unit is given by 1 by second. So we'll go to question 14. In question 14 it is asked that calculate KBC for the operating conditions where UMF is given as 0.02 meter per second and diffusivity, that is D, is given by 2.5 into 10 power minus 5 meter square per second, and epsilon MF is 0.52, and dB, that is the diameter of the bubble, is 4 centimeter, and G is 9.81 meter per second square. Use Davidson and Harrison 1963 expression. So option A, it is 5.14 per second. So in the previous problem only we saw what is the unit of KBC or the interchange coefficient, which is given as 1 per second. So here we are utilizing it. Option B, it is 15.24 per second. Option C, it is 10.55 per second. Option D, it is 12.14 per second. So just pick out the formula to be used and use in the substitute all the given data in that expression and we'll see the answer. So we'll solve the problem. So as always, we'll start with writing the given. So what are all the things that are given. So now we need to find KBC. KBC. Formula we need to use Davidson and Harrison expression. Formula so the formula for this particular is 4.5. Okay, KBC is equal to 4.5 UMF plus 5.85 D 1 by 2 1 by 4 divided by dB will come. So this one divided by again dB divided by 5 by 4, 5 divided by 4. So this is the formula we are using for this particular problem. So now we need to substitute all the known from this problem, from this question into this formula. So KBC would now become 4.5 into UMF, it is given as 0.02 meter per second, divided by dB, that is diameter of the bubble, is 4 centimeter or 0.04. 0.04 meter plus 5.85 into D, it is 2.5 into 10 power minus 5 minus 5 10 power minus 5 by 1 by 2 into 9.81 1 by 4 divided by dB, that is 0.04 power to the power of 5 by 4, 5 divided by 4. So we have found all these things. Now we will substitute all the known things in the given now we have substituted all the unknowns, all the given things in the formula. So now we'll calculate it and we'll find out the answer. So what it is? So it is 4.5 divided by 2. It is 2.25 plus okay 9.81 is 1 by 4 into 2.5 into 1 by 2. 1 divided by 2. Yeah. So this divided by 0.04 power 5 divided by 4. And then what else we have missed? We have missed 5.85. 5.85. It is 2.8938. So what are we getting? Plus 2. We are getting 5.14. 5.14 per second. We'll see if that option is available. Yeah, 5.14 per second is the right answer. So how did we find out the question 14 answer? So question 14 is a very direct question where we are asked to find the interchange coefficient between the bubble and the cloud. So for that question, what are the given? Minimum fluidization velocity is given and diffusivity coefficient is given, or the D, and epsilon mf, that is minimum uh, the wide edge of the bed at minimum fluidization condition is given, and we have the diameter of the bubble dB, and we have G, it's just 9.81 meter per second. So we need to find what KBC is. KBC is given by the Davidson and Harrison formula. I think it is Davidson and Harrison only, right? Yeah, Davidson and Harrison 1963 expression. So according to that formula, KBC is equal to 1.5 into UMF by dB plus 5.85 into D power 1 by 2 G power 1 by 4 divided by dB power 5 by 4. So we know all the unknowns in this particular unknowns, in the sense what are all the given things we substituted in the formula. So we are getting KBC as 5.14 per second. So which option is the right answer? Option A is the right answer. So I think it is clear enough. So just take a minute to analyze it and we'll move on to the last question of the session. So yeah, we'll go to question 15. I think it is clear enough. So in question 15, it is asked that the value of the interchange coefficient between bubble and cloud and emulsion is 4.55 per second and 2.51 per second. Determine the interchange coefficient between bubble and emulsion. So KBE is asked between bubble and emulsion, right? So BE. So it is 3.21 per second option A, or 5.52 per second option B, or 1.62 option C, or option D 4.32. So again for this question as well, we have used a formula in a question to like 2 questions before or 3 questions before we have found the formula for this. So that formula only we should use in this for problem for finding out the answer. So I hope you remember the formula. Just put all those given values in that particular problem and we can solve it. So I'll give you guys a 1 minute. So if there is any doubt, ask or else try solving the problems and we will discuss it in a minute. So we'll see. Actually, I've just written the formula. Now we'll write given 4.55 and 2.51, which is KBC and KCE. So given KBC and formula is this. Now we need to substitute all the unknowns in this. KBC is 4.55 into 2.51 divided by 4.55 plus 2.51. So what answer are we getting from this? Just substitute and let me know the answer. 4.55 into 2.51 divided by 4.55 plus 2.51, it is 7.06. It is 1.6176 centimeter, second inverse. 1.6176 per second. So I think it is the right answer. So yeah, 1.6176, or else we can say it is 1.62 as given in the options. So answer is option C, that is 1.62 per second is the right answer. So these are all the questions for this week's session. If you have any doubts, ask, or else we will just have a quick recap after 5 minutes and then we'll close the session. If you have any doubts, please feel free to ask. Just 5 minutes for recollecting all the events happened in today's class, and then we will discuss what I think there is more one. So just take few minutes and analyze, and then I will give a quick recap and we can close the session. Thank you. So yeah, I guess we will wrap the session by giving a quick recap. This week it was quite problematic as well as theoretical questions were asked. So first, the question was about dispersion coefficients unit, which is nothing but meter square per second, where dispersion coefficient is given by the product of fluid velocity and some characteristic length, which is meter per second into meter gives meter square per second. And in question 2, it was about Schmidt's number. Schmidt's number is nothing but the ratio of kinematic viscosity to molecular diffusion coefficient or diffusivity. So mu by rho g is the kinematic viscosity, and molecular diffusion coefficient is given by d. So the answer is mu by rho g d, and which is a wrong statement regarding mass transfer coefficient. So mass transfer coefficient under a single sphere condition is given by SH. I mean, for mass transfer we are using Sherwood number, which is kg dp y by d, where dp is the diameter of the particle, y is the mole fraction of the particle of the inert component, and d is the diffusivity. So we are taking all the other components except k into the other side, so it gives ka is equal proportional to d by dpy. So it is directly proportional to the diffusion coefficient of the gas, inversely proportional to the particle diameter, and inversely proportional to the mole fraction of the inert component. So question 4, it was about calculating the total exterior surfaces of an individual all individual particles in the bed. So which is given by volume of the bed segment V seg into 6 into 1 minus epsilon bed, which gives the volume fraction of the particles inside the bed divided by phi s into d sphere, where phi s is the sphericity of the particles. So and sphericity of spherical particles is given by 1, and whereas sphericity of particles that are not sphere, that is non-spherical, is less than 1 always. So mass transfer coefficient unit is given by meter per second. So if you want, you can calculate it by using Sherwood number. Sherwood number is a dimensionless number, and it is given by k into dp into y by d. So we know dp is meter and y is dimensionless, and d is meter square per second. So meter by meter square per second, which is giving 1 by meter per second. So since its Sherwood number is a dimensionless number, we can calculate it as meter per second. So answer is meter per second is the unit of mass transfer coefficient. And we asked to calculate the Sherwood number for naphthalene particles by giving fluid velocity, density of gas, and viscosity of gas, and diameter of the particles. We are using Rand's expression. We saw how to calculate it using this given formula, where Sherwood number is equal to 2 plus 0.6 into Reynolds power 1 by 2, Schmidt's power 1 by 3. So on substituting all the given, we are getting Sherwood number as 11.16. And the next question we are asked to solve for the Schmidt's number. Schmidt's number is nothing but the ratio of kinematic viscosity to the diffusion coefficient. So similar way, it is mu by rho g into d, and we are getting the answer as this mu by rho g d, and we got the right answer. And in question 10, it is asked to calculate the Reynolds number of the particle. So particle Reynolds number is given by rho into v into dp by mu, where rho is the fluid density, v is the fluid velocity, and dp is the diameter of the particle. Since we are calculating the Reynolds number of the particles, we are using diameter of the particle as a characteristic length, and divided by mu, which is viscosity of the fluid. So on substituting all these things, we are getting the particle Reynolds number. So again, it is a straightforward question, and in question 11, it is asked that we are asked to find the total exterior surfaces of all individual particles in the fluidized bed reactor. So for this particular question, we use a formula from the previous question, which is S exterior of particles is given by volume of that particular segment of the bed into 6 into 1 minus epsilon bed divided by 5s into dsp. That is the diameter of the spherical particles. So on substituting all the values, we are getting the right answer. So in question 12, it is asked to calculate the correct expression for the interchange coefficient, where KBC, KBE and KCE are given. So basically, bed and emulsion, interchange coefficient between bed and emulsion, sorry, bubble and emulsion, so not bed, bubble and emulsion is given by KBC into KCE by KBC plus KCE. So bubble and emulsion, it is related by KBC into KCE by KBC plus KCE. If we take the inverse, that is 1 by KBE is equal to 1 by KBC plus 1 by KCE, that would be easier for you guys to remember. Once you solve all this and get a direct equation, it is KBE is equal to KBC into KCE plus divided by KBC plus KCE. So question 13, it is asked to calculate the unit of the interchange coefficient between bubble and cloud. It is nothing but 1 by second per second is the right answer. And in question 14, it was asked to calculate the KBE for the operating conditions where UMF, minimum fluidization velocity, is given and diffusion coefficient is given and epsilon MF is given and diameter of the bubble is given and G is given. So we are using Davidson and Harrison expression. So the expression is given in the next slide where it is KBE is equal to KBC. What are we asked? KBC is equal to 4.5 UMF by dV plus 5.85 d1 by 2 g1 by 4 divided by dV power 5 by 4. On substituting all the values in this particular formula, we are getting the right answer. So in question 15, we are asked to calculate the interchange coefficient between bubble and cloud and bubble and emulsion when bubble and cloud and emulsion interface interchange coefficients are given. So on substituting all these values, we are using the formula from the previous problem where KBE is equal to KBC into KCE by KBC plus KCE. So the right answer is we are obtaining as 1.62 per second. The unit is per second. So these are all the problems for this week's session. I hope everything is clear. If you have any doubts, please feel free to mention it in the comments. I'll be happy to take those questions and answer you guys whenever. So that's it for today's session. We'll meet again the next Friday between 6 p.m. and 8 p.m. So and that's it for today's video. That's it for today's class. So we'll log out from the session. Once again, I thank everyone for attending, although no one was there. Yeah, thank you.